Welcome back to Adventures in Climate Change. I am your host, Trevor Snyder, and today we are looking at the part 2, as you probably saw in the title, of Mr. Ellis's Tox 10B Ice Age Modulation Part 2. He obviously has his own channel here, and I mean, he's gained probably 300, 400 subscribers since I've been watching him. And his talks are about all sorts of stuff. So interesting stuff. Really neat guy. I wish I could sit down with him and talk with him in person. I'm not sure where he's located at. He has a bit of an accent, and but super interesting. I actually some of his other videos you'll have to watch, and pretty compelling stuff. I mean, I always think it's pretty compelling stuff. We left off here last time with figuring out that as CO2 rises, dust goes down, right? Because the more CO2 you have, the greater plant life you have, and then everything else follows plant life, right? So, and then the low CO2 creates a lot of dust, and the dust is what sits on the ice caps, which helps, what Mr. Ellis is saying, helps with insulation in the earth. As you're accepting stuff, you're not just bouncing the heat right back out off the ice, right? Reflection, albedo. So I think that's pretty much it. The first video had to do with a little bit of the Milankovitch cycle, which is a part of it. And then albedo and dust is the big thing. And we're looking at CO2 right now. Let's get into it, Mr. Ellis.
Scientists will love to talk about precipitation deserts, dry deserts, but they won't mention CO2 deserts, even though we know they are a possibility, because it goes against their global warming belief system. They don't want to mention something something negative about CO2. And remember, the Gobi Desert lies at high altitude. So the plants there will be running out of CO2 much quicker than at sea level, because there is less air pressure at high altitude. It's like you climbing Mount Everest and running out of oxygen. You do so because there is less oxygen up there. The air pressure is lower. And
that makes sense to y'all? I mean, molecules just move from high to low resistance, right? And gravity comes into play. So as you get closer to the Earth, the gravity's just pulling a little bit more. Molecules in the air are a little bit more dense. They're sitting heavier, and the air is denser as you get closer to water level than it is up by Mount Everest, right? Like what he's saying. And so this makes complete sense. Something that I take for granted, right? You don't think about all the time. Elevation.
The plants on the Gobi Plateau will do exactly the same. They will be affected first before any plants at low level. And so the Gobi Plateau will become a CO2 desert. Its soils will be denuded, and they can be eroded by winds and then blown across the lowest plateau, as we know they were, and blown across the Laurentide and Greenland ice sheets, as we know it was. And just to show you how much dust there was, this is an image from Greenland, which shows ice age dust in situ there, actually now, today. So just to show you what this image is showing, to the right we've got ice that was deposited, say, 25,000 years ago, quite a long time ago. And as we progress to the left, as you look at it, so that ice gets younger and younger and younger. And then we hit the double band on the left there, which is the Younger Dryas, and that was about 13,000 years ago.
Okay, so
so you can see how much dust.
And he's saying this is the really dusty stuff, right?
Ice. And remember, this is way up in Greenland. This is much further away than the Laurentide ice sheet. They estimate that on the Laurentide, there was something like 10 times or 20 times as much dust deposited as here up in the high Greenland ice sheet. So the Laurentide ice sheet would have been much darker than this. And remember also that this dust gets concentrated as the interglacial proceeds, as the ice starts to melt.
It sits on top of other layers.
We've said before, the ice melts, it can melt, it can ablate, but obviously the dust can't, and it remains on the surface. And so the dust we see here on this ice sheet in Greenland can be concentrated until it looks something like this. And it can go even worse than that, because this is me up on the Baltoro Glacier up in the high Himalaya, and I'm standing on a glacier.
You look so
on
young.
An ice glacier.
Ice glacier. Glacier.
And it might not look like a glacier, but most glaciers don't look like an icy glacier as you traditionally think they will look. Because
I grew up in northern Idaho, also, in addition to the Bay Area. And in northern Idaho, we go to Glacier National Park in Montana quite frequently, and it's one of the coolest things. But the glaciers aren't exactly what you think of as glaciers, because most of the snow and ice has been covered with dust and dirt over years and years and whatever. So a lot of the frozenness is underground, as we say. So
the ice on the surface gets ablated, it gets melted, and all you're left with is the stones that have fallen on top of the glacier. And so I'm standing on 100 meters of ice, but all you can see is the top layer of stones and dust that are still concentrated on the surface.
It's true.
And it's that dust that lowers the albedo that causes the melting. So now we have a complete mechanism for the Ice Age cycle, which has never been explained before. Nobody knows how the Ice Age cycle works, which is, in the 21st century, that's quite amazing that scientists still don't know how the Ice Age cycle is modulated and operates.
We're too arrogant.
But now we do. But only because you tune into the Illumination lectures. So this is how the Ice Age cycle works.
Tune in.
Here is a graph of an Ice Age cycle. And you can see from the peak in the red is the temperature plot. The peak in the red is an interglacial. It's very warm. It's like it is now. We are in an interglacial now. But then the blue plot, which is the insolation plot, that's the orbital cycles changing the temperature in the northern hemisphere, changing the amount of insolation, the amount of sunlight in the northern hemisphere. The blue plot plunges, and you can see that here, that the blue plot goes down quite low. And that's quite a difference. It's like 20% change in the amount of sunlight.
Wow.
Hitting the high latitudes
that makes
of
sense.
the northern hemisphere.
You get the tilt change.
And the temperature cools, not surprisingly. And so the red plot plunges in line with the blue plot, and we get cooling in the high latitudes in the Arctic. Because remember, this only operates in the northern hemisphere. It doesn't operate the same in the southern hemisphere, as we said in the last lecture.
And just to revisit that's because almost all the land masses are in the northern hemisphere. I mean, I forget what he said, but it's something like 70% of land or 75% of land or something is in the northern hemisphere. That's where the ice can land on. It doesn't typically get formed in the ocean, right? That's the byproduct of it forming on land and going outward and landing on itself. So when you have an ice age, it only really forms, like at least the giant ice glacier sheets form on the northern side.
So we get ice buildup in the northern hemisphere. We get ice across the continents, across Siberia, across Northern America. We get a buildup of ice. And this ice is highly reflective, and so it can reflect the sunlight, the incident sunlight, back into space. It has a high albedo. And so this acts as a cooling feedback. You're getting less sunlight because we're going into a great winter here in the northern hemisphere. And the ice is reflecting any sun that does come in, and it's causing more cooling. So you get this cooling feedback, more ice, more cooling.
Effect.
And that generates an ice age ice sheet. And so we get this cooling, which, as you see in the red plot, goes on and on and on for 100,000 years. And during that 100,000 years, we do get more orbital cycle maxima. We get these Milankovitch maxima, what I call a great summer, where the amount of insolation, the amount of sunlight in the northern hemisphere increases. And you can see that in the two blue peaks halfway down, we get two quite large increases in solar sunlight hitting the northern hemisphere.
I wish they had years at the bottom of there because, he keeps mentioning things. It almost makes it sound like this is happening in a year, but it's obviously not happening in a year.
And it does virtually nothing to the temperature.
Mm-hmm.
Why does it do nothing? Well,
right here,
because the
right
ice is bright white, high albedo. It's reflecting all of that incident sunlight away. So this cooling goes on and on and on. And effectively, it could go on and on and on until the Earth entered something like a snowball Earth, where most of the Earth was covered in ice.
Neptune.
So we've got to have some mechanism of stopping this increase in ice. And that comes about by CO2, because as we saw, as the world cools, temperatures fall, which increases oceanic solubility, which reduces CO2 in the atmosphere. And so CO2 goes down alongside temperature until it hits 180 parts per million at sea level. But high up on the Gobi Plateau, that's the equivalent of 150 parts per million. And that's enough to kill off all the plants and cause a CO2 desert, that term that they don't like to use. And it is this CO2 desert that causes the dust. As we saw, and as we can see here, you get a very large peak of dust. It's not just a small increase in dust, it's a huge increase in dust. And it's not just dust for a couple of years, this is dust for 10,000 years. And why for so long? Well, because the climate system is waiting. It's waiting for an increase in insolation again. It's waiting for another great summer. And so as soon as that increase in insolation comes along, as soon as we enter that great summer, the lower albedo ice now, because it's covered in dust, can melt. It can warm and melt. And it concentrates on the surface as it does so, increasing the concentration of dust and therefore increasing the warming feedback that the dust is given.
It does make sense.
And so we can have complete warming in 5,000 years, because these interglacial warming periods are very, very short. So we have an ice age for 100,000 years, say, and then the interglacial just takes 5,000 years to melt all of that ice, because we have this very, very strong feedback caused by ice albedo, by the dust getting on the ice sheets. So that is the ice age cycle. And in conclusion,
we should keep the CO2 up.
What we see is something that has a great contrast to what we're normally told.
It is.
It's actually low CO2 that causes global warming during the ice age cycle, by getting so low that the plants die off, causing dust.
It starts at higher elevation.
It's a very easy theory to understand, but it's never mentioned because it goes against the global warming industry or religion that they have created.
I call it a religion too.
Sorry, no. Let's put it the other way around. There is no money to be made in albedo, but there is lots of money to be made in CO2,
carbon capture
feedback, because your taxes are increased, your energy bills are increased to try and mitigate this non-problem, and that money is flowing into the pockets of the green lobby. Climatology used to be an obscure branch of science located in a hut at the end of the university campus. But now, quite often, climatology, global warming, is a major spinner, money spinner, in universities and university grant systems. The last thing these institutions want you to know is that global warming during the ice ages is controlled by albedo, by dust on ice, and not by CO2.
Right. And the CO2 does play a role, but only in the fact that giving life and whatnot. And once it's depleted, that's when the dust comes out. He's only got a few seconds. I'm sorry for interrupting.
Well, I hope you've enjoyed this illumination lecture, and I hope you can join us again next time. Thank you.
Wow. I didn't think we were going to get his premise at the end. I thought he would kind of leave it blank, and he really brought it full circle and gave us a conclusion. I mean, a few sentences right at the end basically said it all for me, and I know a lot of people are going to be upset. Okay? They're going to be upset. They're going to be like, okay, no, this guy's got to be wrong because of the CO2. I'm telling you, this stuff, the way he explains it makes sense. And it actually goes into, I have my, it's just a bachelor's degree. I have it in health science, but it was in biology emphasis. I loved biology and physics and chemistry and whatnot. I just didn't see a future economically in it. So that's what my degree's in. So I tend to like those type of videos, like reading about that type of stuff, figuring it out. I'm a science guy, even though in fact I think most human beings are science people. They just don't realize it. We all perform different experiments in our own ways for our own reasons. But I really liked how Mr. Ellis really brought it full circle and was just like, carbon capture is the biggest moneymaker right now. And we've seen that it's not that great building batteries and constantly having all these cars on batteries when these cobalt, these tin mines, these everything, they're primarily owned by the Chinese, but it's slave labor. It's basically slave labor. So it really kind of, when you look at the big picture of everything, it's like, okay, what is going on? And should we be doing this? Should we allow our taxes? The heating bills are this much more because of everything we're doing, the demonizing of the petroleum products and everything. And so, look, I just think there needs to be a better balance. I'm an advocate for that, and that's how it is. So I hope you enjoyed this video. I really enjoyed these ones with Mr. Ellis here, and I thank you, Mr. Ellis, for laying down that comment for me to actually go down this rabbit hole. Check out we did a video on your article that you did. We did the videos on these two, and he does a lot of videos on just random type of stuff. You need to go check it out. If you don't mind, please, I'm begging you for a subscription. I love the subscriptions, just something about that positive feedback, right? I do like likes, but if you didn't like the video, dislike it. It is what it is. I get dislikes too, because this is a controversial subject, and it's okay. I completely understand if you don't like what I'm saying. I totally understand, and feel free to give me a dislike. Otherwise, I do appreciate the likes, and I'm excited. We'll catch you on the next video.